Good afternoon, everyone. Thank you for joining us this month for our monthly webinar. We're happy to have all of you here. Today, we would be continuing the series we started last month. We spoke on, we had our presenters share the experience of the LINAC commissioning at the Asiupo Cancer Center, Calabar. Today, we'll be having another medical physicist share a similar experience. So our speaker today is Mrs. Temitope Orotoye-Sanusi. She's a medical physicist at the Marcel Ruth Cancer Center, Lagos. Yes, I think she would introduce herself further if she has any other thing to add. Thank you very much, Tope, for joining us today. Thank you for honoring our invitation, and we are ready when you're ready. Thank you. Please, if you have any questions, you can kindly put them in the chat while she speaks. Thank you very much. Over to you, Tope.
Thank you, Dr. Yebisa. Good afternoon, everyone. I hope I'm audible enough.
Yes, we can hear you.
Okay.
Please, you can share your screen. Yeah.
Okay.
Okay.
Good afternoon, everyone. My name is Temitope Orotoye-Sanusi, and I'm a medical physicist at Marcel Ruth Cancer Center, Victoria Highland, Lagos. So this afternoon, I'm privileged to be the one that will be sharing with us our experience during the commissioning of our linear accelerator at Marcel Ruth Cancer Center. So before I proceed, I would like to introduce the team of medical physicists that carried out this commissioning process. So our chief medical physicist is Dr. Michael Akuchafo. Then we have the lead medical physicist during the commissioning. We have Dr. Harun Chemadurai. We have Mr. Maruf Hadewale, and also myself. So we had a team of medical physicists that actually carried out the commissioning process of our linear accelerator. Okay, so this is our center, and you're welcome to Marcel Ruth Cancer Center and Specialist Hospital. Like I said earlier, we are located at Victoria Highland, Lagos, and you're free to visit us anytime you come to Lagos. We'll be glad to have you. So before I go into the main topic of the day, which is our commissioning experience, I would want to talk briefly on some procedures that need to be carried out before a machine, a linear accelerator or a radiotherapy machine can be released for clinical use. So the first thing is installation of base frame, because we are making use of a linear accelerator from Nigerian medical system. So we install the base frame. Base frame is like the foundation. You know, when you build a house, you have to have your foundation done, and that foundation is very important. So the installation of base frame is like the foundation for linear accelerator installation. This helps us for accurate positioning of the linear accelerator in relation to the patient couch. Then after this is done, there will be some time. After this is done, then the installation engineers now start with the installation of the linear accelerator itself. So this also takes, it takes the time, like it takes a lot of time for that to be done. And the moment your linear accelerator actually produces the first beam, then that is at the completion of the installation. Then we go to, or we proceed to the next phase, of the preclinical procedure, that is the acceptance testing. So what is acceptance testing? Now, during this acceptance testing, there are some things that are done. We carry out performance specifications, because there are some specifications that have been, stated even before you acquire, when you want to acquire your machine. So at this point of acceptance testing, we try to verify the performance specification of the machine. Now, this is not done by the installation engineer alone. The medical physicists also join the installation engineer to carry out this acceptance testing. So we do a lot of tests are actually carried out. Then reproducibility test, the light field, a lot of tests like that, just to ensure that the performance specification is met. And also during this acceptance testing, there is need for what we call radiation monitoring. Like you have to monitor the environment to ensure that, okay, by the time the accelerator is being put into use, then the environment is actually safe for everyone to work. So that is what we do during acceptance testing. This is a very important test. Now, after this acceptance testing, before our commission starts, we do absolute dosimetry. That is before the proper commissioning. Now, after this is done, then we move to the commissioning phase. So during this, I would like to tell us that, like as we already know, that commissioning is done just once throughout the lifetime of a machine, and we cannot afford for error to take place. So this commissioning process has to be done very accurately and also carefully, so that there will be no room for error. Now, when commissioning phase is completed, then we move to the training. You train the staff on the machine, how to make use of the machine. And when these all procedures are completed, then we can now, our machine will now, we can now start using it for clinical procedures. Okay, now the radiotherapy equipment that we have at Marcel Road Cancer Center. Okay, we have a GE simulator, a GE Discovery, like is the CT simulator that we have. It's a large bore. It has 64 slices, and it also has lab laser. Then our true beam linear accelerator. At this point, I would like to, it's not about bragging, but that is just the truth, that our true beam linear accelerator is the only one we have in Nigeria as at now. That's the only one we have in Nigeria, and the only one at that in the whole of West Africa. So this true beam linear accelerator is equipped with 6 photon energies and 5 electron energies. We have the 6 MV, the 10 MV, the 15 MV, and the 18 MV. Now, it also have platinum filter free energies. That is the 6 MV platinum filter free, and also the 10 MV platinum filter free. Our true beam linear accelerator is also equipped with Millennium 120 MLC and has 6-degree freedom for couch movement. Now, this linear accelerator is also equipped with onboard imagers. We have the KB, we have the MV, we have the CBCT, just for proper imaging before radiation treatment is carried out. Now, this is equipped, it makes use of 2.5, like 2.5 energy. And the Eclipse treatment planning system we have is of version 16.1. And that is the latest Eclipse version that we have as at now. Now we have the the treatment algorithm that we have, the dose calculation algorithm. We have the anisotropic analytical algorithm, that is the AA, we have the Accuracy. Then it also has the electron Monte Carlo, that is for electron planning. Then we also have algorithm for the Porter dose imaging. Sorry, I did not include, but we have algorithm also for the Porter dose imaging. So commissioning itself, what is commissioning? It basically, or in summary, commissioning is a process. It involves a lot of comprehensive measurement of dosimetric parameters. So that is just a phase that you need to do. Like, it involves a lot of tests just to ensure that your machine is ready to be released for clinical use. So it involves a lot of steps: importing, calculating, verification of data. So you acquire data from your machine, from your linear accelerator. Then you import this data into the TPS system. you process it to ensure that the dose calculation algorithm can accurately represent your beam energy and you have proper or accurate dose distribution within your target. Now, this is also very important because any error that is made during this commissioning process will affect everything, like every treatment, all through the lifetime of that machine. So that is one important reason why there is no error, there is no room for error during commissioning, because any error done at that point will affect the quality of your treatment outcome. Now, if there is any error, that means you might be underdosing your patient, or you might be giving them more dose than necessary. So it affects the quality of your treatment. Once your commissioning phase is okay, like is very okay, then you can be sure of the quality of the treatment you are giving to your patient. Okay, just like I said, it involves a lot of data that will be collected, a lot of dosimetric data, and this data include, we have the PDD, the beam profiles, the output factor, dynamic wedge data. All these are data that you actually acquire during the process of commissioning. Okay, so for this commissioning process, what are the equipment that we made use of during the commissioning? Okay, we made use of the ionization chambers, the electrometer, coaxial cable. This actually connects your electrometer to your ionization chamber inside the bunker. Then for absolute dosimetry, we have thermometer, barometer. Now there is the radiation field analyzer. That is the 3D water phantom, like it's a water phantom tank, and it has 3D dose view software. Now this 3D phantom is actually produced by Standard Imaging. Then electron applicators. Then we also have EPID, that is the electronic portal imaging device. So for your dosimetry, all your measuring device must have some basic characteristics, which is very important. Your dosimetry, your measuring device must not be energy dependent. So it's not like, oh, okay, it must also be very sensitive. Then there must be negligible leakage. Those are some of the characteristics that your dosimetry device or your measuring devices must have. Now, this figure is just what we have here. We just have pictorial representation of the ionization chambers. Now, this is the plane parallel ionization chamber. This is the pharma ionization chamber and the pinpoint ionization chamber. This actually has 0.125 cc. That's the measurement, and we have the electrometer here. So this is an applicator holder, and these are a set of applicators for electron. Okay, now dosimetry setup. This is the setup for our commissioning. You have to set up before you start acquiring your data. We have the 3D water phantom here that has the reference. This is actually the reference chamber, and we have another chamber also in the field. The gantry must be at 0, and this is just the water tank. So you use this setup. When this setup is done, when we have this setup, we also acquire. That is what and this is how we set up our dosimetry equipment to acquire our data, the PDD, the beam profiles and everything. Now for the beam profile can be in 2 diagonal, like the X and the Y axis. And for the dose curve, it's at square centimeter, like 2 by 2, 10 by 10, 6 by 6, and like that. So the beam profile is actually acquired for all field sizes. And the output factor is also acquired for like 2 by 2 to 40 by 40. Now for the output factor, one of the reasons why this output factor is very important is because it helps the TPS to actually determine the phantom scatter, because we have total scatter, we have collimator scatter. Now, when a patient is to be treated, we want to ensure that, okay, all the dose, like everything gets inside the patient. But the thing is, because of collimator scatter, we have some radiation that will actually be in here. So we need to calculate this and that is why the output factor is very important. So we acquire the PDD using extradin H28, that is the pinpoint. It has 0.125 cm Q. Now, we have specified references for different photon energies. Now, there are some other things we actually acquire apart from the beam profiles and the PDD and the output factors, such as the MSC lead gap and the transmission factors. Now, this is carried out at 20 by 20 field size. Okay, now when all these data are now acquired, we actually we converted it in Eclipse format, like from the dosimetry laptop. Just like I said here, this 3D water phantom is actually controlled by a software, and that is how we, on the software, we actually input all the things we want to measure. That is how we acquire all those data. Now, this data will now be processed and converted into the TPS, the treatment planning system, for commissioning of each of the algorithms. Like I said earlier, we have the AXV, we have the AA, and we also have the EMC. So when it is processed, it is converted in Eclipse format, and we process each of these data for the proper commissioning. Okay, so I would just like to show us a set of PDD profiles that were measured during the acquisition of the beam data from the machine. Here we have a set of measured PDDs. These images are acquired from the software that we used for dosimetry. Then we have the measured profiles for the photon energies, 6, 10, and all the flattening filter-free energies also. Then we have a set of PDD for the electron. Likewise, measured profiles for the photon energies. So when we acquire this data, what will we do with it? We want to use it to commission our TPS system. TPS is actually a treatment planning system, because when you want to treat a patient, you calculate the dose. And what does that? It is our treatment planning system. Now, this is showing us the workspace of the treatment during the commissioning of the treatment planning system. And sorry, I want to show us something. Okay. Sorry, I couldn't bring that image up. I wanted to show you the acquired data, like, because when the data are acquired from the machine and it is processed, I wanted to show you us the format before we now input it into the treatment planning system. Okay, so these are all the things that we need to do, and this is just a sample of the 6 X flattening filter free. That is the 6 energy photon, the flattening filter free. Now we do all this. We input all this data for the general parameters, the module parameters, all these parameters, and we have to import data for each of this, for each of the energies, the measured diagonal profiles, the depth doses, output factors, and like that. So that is why it takes a lot of time. Like in our center, we use 2 weeks, and that is the fastest commissioning that, like, so far. We used 2 weeks, but those 2 weeks were not just 2 weeks of day. They were 2 weeks of both day and night. Like, we actually use days and nights for our commissioning, but we used 2 weeks, about 2 weeks in total for the commissioning process. So all this takes a lot of time, because you have to do this for each of the algorithm, the treatment planning algorithm. Then also you have to do for each of the energy, you have to do for each of the field sizes. So you can imagine trying to process all this data for one energy, for each of the algorithm and everything. So that is why commissioning process actually takes a lot of time. Now, this is showing us a comparison of the calculated depth dose and the processed measured depth doses. And as you can see, like, everything is in, like, it is well comparable. And it's showing us the diagonal profile for the calculated, and also when it was processed in the treatment planning system. Now, this, I just showing us a set of depth doses, like already processed in the treatment planning system for the depth doses. We have also for the diagonal profiles. We have also for measured profiles. Like I told, everything has to be done for each of these energies. Now we have the output table, output factor table here. And this helps the treatment planning system to be able to account for the phantom scatter, because we have the phantom scatter, we have the total scatter, we have the collimator scatter. Now we cannot measure this phantom scatter right there in the inside the bunker, like in the machine. We have the TPS has to process to get us for that of the phantom scatter, and that is why we need the output factor. And this is showing us the output factor table. It involves like for different field sizes from 2 by 2 up to 40 by 40. Now, the next thing is, after that has been done, we actually carried out the commissioning of the IMRT and RapidAct. These are complex treatment techniques that you need to use, or that we use in our system, and it is very necessary that you commission these treatment techniques in the TPS. So what we made use of was the electronic portal imaging device. So it was mounted like on the gantry, and the robotic arm of the gantry at 40 by 40, and the resolution was 0.336. That was, and for the, so control point with MLC positions were calculated for a dose length. And for RapidAct, positional accuracy of MLC, positional accuracy of MLC in RapidAct mode, deviation and deviation of MLC, all these data were actually acquired during the IMRT and RapidAct commissioning. And the next slide now, I would like to show us a video of the IMRT fluence that was calculated in the treatment planning system and how it was delivered, like comparison of whether our commissioning was, okay. So it was just like trying to see. So at the treatment planning system, I would like to show us the video of the IMRT dose fluence. So MRC was planned in the treatment planning system, and that is what we want to deliver here. And this video is showing us how this is being carried out even there at the machine. So the dose is being delivered, and we can see as the fluence is going on. So we want to get MRC, and that is what we are seeing right on the screen. Yes, so we have MRCC delivered according to plan. Thank you. So this is the gamma analysis that was carried out, because after that, we need to do gamma analysis, like doing patient-specific QA. It is very necessary for all your complex treatments. You do that for RapidAct and also for IMRT. And this actually gave us, the gamma analysis gave us 99%, which actually passed. So, and we have for RapidAct here, the same thing, we have 99.6, and these are just images of RapidAct portal dosimetry, because since we wanted to see the efficacy or how efficient the EPID was for commissioning of these complex treatment techniques. Okay, so after the after the commissioning of the TPS, we need to do verification also. So there are some steps or some things we also that we carried out. That's like the point dose, the hand-to-hand testing. All these are to verify the accuracy of the commissioning of the treatment planning system. So the point dose measurement is just trying to get the absorbed dose at different points, in the target. I would like to show us something so that I would be able to compare the measured dose with that of the TPS commissioning. Okay, now this is the results during the point dose measurement. So we had to do for different energies at for different field sizes, both symmetric and asymmetric. And we had to calculate at different depth to know and compare the measured dose with the treatment planning dose. So, and everything here, the deviation is actually less, majority are not even up to 0.5% deviation that we have for the point dose measurement. And looking at all this deviation, then at least we've been able to verify that okay, our treatment planning commission is okay. So I would like to go back to my slide now. So I'll stop the sharing of this particular page. Okay, so after the point dose measurement, another verification test we carried out was end-to-end test. So how did we do? End-to-end test is just like mimicking a proper treatment from start to end. Now, using the phantom, ionization chamber is placed within the phantom and simulated. The phantom is simulated with the ionization chamber placed in it. Now, the images are acquired and planned on. We calculate the dose. Then this particular phantom with the ionization chamber will be taken for treatment. The dose that is measured by the ionization chamber during treatment is now compared with that which we have at the treatment planning system. And when we compared it, it gave us, it was comparable. And that is one of the verification tests that has to be done to be sure that, okay, your TPS commissioning is very okay. Because you have to ensure that all these are done, everything is accurate before you can now release confidently the machine for treatment. So also, we also ensure that we carried out, like we planned on different phantoms for all the techniques that we'll be using. You know, we use 3D, we use IMRT, and we also use VMAT. So we also did this like just to verify that, okay, all our commission for all these techniques are right in place. So we also did for IMRT using the CAT phantom, and we have also for VMAT. We did this just to ensure that all these techniques, everything is okay. Like we need to double check and double check and double check. Now, after this, we do absolute dosimetry. Remember, we have to do absolute dosimetry even right before the commissioning process starts to ensure that, okay, to tune and everything is okay for the machine before commissioning starts. But after all this again, we have to do absolute dosimetry again. So the protocol we used was TRS-398. That was what we used to do the absolute, the protocol that we followed to carry out the absolute dosimetry. And the reference field size at 10 by 10 cm, and the SSD was also 100 SSD. Now, this is the result for all our, the absolute dose that was gotten for all the energies. And everything is within acceptable limits. Like everything is just that one gray was giving us 1 gray for all the energies. Likewise, that of the electron also. And after all this, it shows that our machine output is within acceptable limits, looking at all these results that we have. Now, after this, we go on to MPC. So now, for this absolute dosimetry, that is what we use to set the baseline. You know, we used to we tune the machine to now set the baseline for after this absolute dosimetry, looking at all the results that we get. After this is done, then we go on to what we call machine performance check. Because we use a Varian system, the TrueBeam LINAC is manufactured by Varian Medical System. So because of that, Varian now has a kind of like machine, call it a machine performance check. It is not to, it is not that, oh, we use this to replace QA, but it's just a kind of test that is carried out more like to just keep assuring the quality of your machine. Now, after dosimetry is carried out, then we do MPC. This MPC we check for, we do mechanical tests, and we also carry out dosimetric tests during this MPC. And this is done daily. So this is the setup of the MPC. We have what we call the MPC phantom, and it is positioned at a particular point on the couch, H2. So this is just generally the homebody images we call, you had the energies, but all those processes automated. And this is the check report for the MPC. Looking at it, everything is within threshold. Now for this MPC, your tolerance must not go beyond, it has to be within plus or minus 2%. Everything must be within plus or minus 2%. Like I said, we just check it. It checks automatically for you a lot of tests, the beam, collimation, reproducibility, and everything. So all these are actually carried out. Now, when we are done with all those tests, we now come up with a QA procedure that has to be done routinely, like we do them routinely just to continually assure the quality of the linear accelerator. Now, once this is completed, the machine can then be released for clinical use. But one thing that is common, I think, is that during this process, because the machine has beamed during the period of acceptance testing, everybody feels, oh, this machine can now start working, let us start treating patients. There will be a lot of pressure on medical physicists. In fact, here there were a lot of pressures like, okay, the machine can start treating because it has beamed. No, a lot of pressure will be on the medical, but you as a medical physician, like, no, until this is done, we cannot release the machine for clinical use. And at this, during this phase, you'll be so happy that, oh, you are a medical, because they keep asking, physicists, is the machine ready now to be used and hauled? But you have to be very careful because nothing must go wrong with the commissioning. If anything goes wrong with the commissioning, it affects the overall quality of the treatment. So it is very, very, very important. And with this, I would like to say thank you for your time, for giving me the opportunity at least to share our commissioning experience with you at Marcel Ruth Cancer Center. Thank you, and thank you so much. And these are just set of pictures. We have this particular picture was taken after the acceptance testing. So we have the medical physicists with the installation engineers, and during our commissioning, in fact, we have the governor even joined us to see how important this phase is to treatment. We have the governor also join us. We even have our CEO even join us at that to see how important this phase is. And we have, we are the physicists at Masaru Cancer Center. This is Dr. Mike Akuchafo. This is Mr. Maruf Adewale, and this is Dr. Aaron Chamadurai, and this is my humble self. So thank you so much for joining us.